Shanghai GDG is a very interesting developer community.
I'm glad somebody has asked this question.
This is where the magic happens.
This is primarily a question and answer show. So if any of you out there would like to ask questions.
All right. Welcome, everyone. Thanks for joining today. My name is Fred Sauer. I'm a developer advocate working on App Engine. And with me today,
Ayin Valdez. I'm also a developer advocate working on Google App Engine.
So today we thought we'd talk to you a little bit about load testing on App Engine and some performance tuning tips. So how to get prepared for when your app is finally successful. So I want to start off and just share with you a few graphs from one of our customers. I picked out some of the bigger events that they had. This is a company that does social events. So they have a gadget that they put on other people's websites, and people can chat on this gadget and interact with each other. And depending on the excitement of the event, be it a sporting event or something like that, different things happen to the traffic patterns. So at any point, when you're looking at the traffic graphs, you don't know what it's going to do next. Is it going to go up? Is it going down? Are you going to get 10x the traffic that you had a few minutes ago, or are you going to get half the traffic? And so you see the graphs here, and a couple of interesting things is that, well, these are the most popular events. Between the smallest one, I've left out the Y scale here, but there's a 10x difference between the largest event and the smallest one shown here. The other thing is, if you look at the time scale, this is over several hours. So even though that there's really kind of sharp increases, if you were to zoom in kind of on a minute scale, you would still see what we call kind of a gradual ramp, and I'll come back to that.
So these are good graphs, is what you're saying? Like this is ideal performance?
This is just input to the system. This
Okay.
is customers showing up on your website, knocking on the door and saying, I want to do something.
Right, but in other words, it didn't like drop off to zero. In other words, it didn't
Exactly.
lock up.
This is success.
Okay, that's
Yes.
yeah. So these are good graphs, I guess.
Yeah,
Okay.
and then on the edges of these graphs, there's pretty much nothing going on.
Okay.
When the gadget's not live on an event, there's pretty much no traffic. Just a little bit of background. People refreshing maybe a home page or something like that. So App Engine is this distributed computing platform, and to really understand how it works and do performance tuning and understand how your load tests are kind of flowing through the system, you need to kind of break apart the different components and understand why we call it a distributed system and why that's really important to the characteristics of App Engine. So if you kind of look here from left to right, you have the clients that are producing traffic, so web browsers, mobile phones, and they're sending requests into App Engine. And the first thing they do is they hit the front-end servers. These are the servers that take care of opening up the HTTP communication with the client, serving the responses, and then they direct the traffic down deeper into the depths of the Google App Engine network and onto other servers. You may have back-end servers. You may be using the data store or Memcache, or maybe the image manipulation service. And so each time you make a call, you're going from an app server, which is running your code, down another layer into data store, Memcache, etc. Now, to just to zoom in a little bit on the data store there, when you write an entity to the data store, say, and then that makes an RPC, a remote procedure call, to a tablet server. And that tablet server is responsible for a chunk of your data. And that tablet server then has to write to physical disk. So I haven't listed all the layers here, but you see we already have after the client, we have a front end, there's an app server, there's a tablet server, then there's the physical disk, and there's a few more bits of infrastructure in between there.
I guess the thing to point out is that the front ends and the tablet servers and all that stuff is auto-scaled for you. You don't really actually have to manage it. So whether you have one request coming in or 10,000, that is all scaled by the infrastructure.
Exactly.
Right? Okay.
And so our mission today is to understand how to utilize this infrastructure in a way that it continues to scale for us, that we don't use anti-patterns where we actually kind of defeat the system and turn it into a non-distributed system. Because that's really the one way in which you can hurt the performance of your application.
Cool.
So we'll talk about that a little bit more. So still zooming in kind of on the data store. At the very lowest level, every entity that you store in the data store is ultimately stored in a big table row in this giant key value store. So every entity that you have has a key, and then in the data portion you have all the properties, the values of your entity. Even the index entries are in this form. So if you have an entity, say a customer, and you have a first name and a last name, and both properties are indexed, you'll actually have one row in this table for the entity, you'll have another row for the built-in index entity, and then you'll have 4 different rows for the property. You'll actually have a first name ascending index, descending, a last name ascending and descending. So think of your data as spread out in this giant table of key value pairs. And every bit of data is addressable by a key, and then there's some data associated with it, which is useful. Now this is really important because different parts of your data live in different parts of the disk. And in order to kind of take advantage of this distributed nature of App Engine, you need to make sure that not all your requests from all your users are going to a single block of data on disk. Because if you do that, there's ultimately somewhere in a Google data center, there's a server that is responsible for, let's say, this little red block of data right there. Just these few rows of data, there's one server that's responsible. And it has to be just one server because we want to allow atomic transactions on that data. So think about it that way. Now imagine that one of these rows of red data is some global state in your application. Maybe it's a page counter. And every time a visitor comes to the site, you want to increment this counter and record the fact that you had another visitor. Now let's say you are very successful and you're serving 1,000 requests per second, maybe 10,000 requests per second. All of those requests have to then funnel down from all these different front-end servers to all these different data store servers, all the way down to the single tablet server, which is now very much getting overloaded because it's having to write to disk 10,000 times a second. And if you know anything about disk hardware, you know that that's just simply not possible. So one of the key strategies in utilizing App Engine is making sure that you distribute your load. So if you wanted to have this page counter and you wanted to be able to update it at say 10,000 requests per second, that's absolutely possible. You just need to distribute it over many different blocks of data. And this is a strategy called sharding or partitioning. And what you do is you say, well, instead of having one counter that we store in one row in the data store, let's make 1,000 counters. And let's kind of randomize the keys, or they don't have to be truly random, they just have to be kind of distributed over key space. So just for the sake of argument, let's say we had 26 keys. We could prefix our global page visitor counter with the letter of the alphabet. So we could have A page counter, B page counter, C page, all the way to Z page counter. And then anytime a request comes in and we want to bump up this page counter, we pick one of the keys at random. It really doesn't matter which one. So we could just take a random function times 1,000 or 26 or however many counters we have, and then we update that row. And now what suddenly has happened, instead of having 10,000 requests going to a single tablet server, we've distributed over, say, 1,000 tablet servers, each one doing only 10 requests per second. That's maybe a lot more reasonable.
So you're basically reducing the lock and write contention over a set of keys by distributing it out. So it's a sort of a fan-out pattern.
Exactly.
To increase the amount of concurrency, I guess, in the system.
Yep.
Yeah.
So you can see that what we're kind of saying here is that App Engine has this massive distributed infrastructure for you, but you can definitely defeat that infrastructure if you send all your writes to a single key, if you choose your keys poorly or choose your indexes poorly. So there's a little bit of, I guess, forethought that needs to go into kind of choices of your design. And you do that, and then everything scales very nicely.
And when we talk about Bigtail, or the picture we have here, we're talking now in the new world, sort of in the high replication data store world, which is, there's also issues you have to worry about in terms of consistency and how you structure your entity groups and whatnot as well.
Yeah, there's definitely some design choices to make beyond just selecting your keys.
Yeah.
You talk about consistency, so App Engine has this notion of entity groups. These are groups of entities in which you can do atomic operations. So you can create a transaction and you can manipulate multiple rows or entities within that entity group in a single transaction. And then new, well, not quite so new anymore. It's probably been about 6 or 8 months now. We have cross-group transactions, XG transactions, which if you're a long-time customer of App Engine, you'll remember the day when you can only transact on a single entity group. Now you can actually do up to 5 entity groups in a single transaction.
So it's transactions across entity groups, and so this is really nice for those complex transactions. Yeah.
Yeah. The canonical case is I have money in 2 bank accounts and I'd like to transfer money. I want to deduct $10 out of this account and add $10 to that account. I want to do it in a single transaction, and you can do that.
Very cool.
So there's a number of tools that App Engine provides for your tools for the trade. One of them is called Appstats, and actually in the 1.7.1 release that just went out last week, there's an enhancement that's not even represented here in the screenshot. There's a little shell mode that allows you to type a snippet of Python code and actually see what the Appstats would look like for that without having to deploy your application or test it. So you can work on snippets of code and optimize them. Now this is a great tool. I love the quote here. I used to be blind and now I can see. And what the person meant here is that they used to be blind to kind of what was going on in their application. They could certainly read through their code and see how many data store calls they thought they were making. But when you turn on Appstats, you actually get a visual overview, and you can see that in this case, there's kind of this staircase effect where one RPC happens after the other, and that actually slows down the request quite a bit. And it gives you hints. I guess looking at this, you can say, maybe I should use some asynchronous fetches so I can do more things in parallel. Maybe I can do a more efficient query.
You can batch requests together, so you can make one round trip versus 100 if you wanted to fetch 100 entities, for example.
Yes, exactly. So first thing you should do if you're optimizing your application is turn on Appstats. You can use it in the development server. You can use it in production. If you don't want to turn it on for all of your live traffic, you can deploy to a separate version, a non-default version of your application, and turn it on there and then just play with it yourself. So let's start off with kind of some load testing guidelines. First of all, your load test should really be representative of the real traffic that you expect. And that just doesn't, that means kind of the rate at which you on-ramp traffic. You should let traffic ramp up over many minutes. When
you don't just have a million users come to your site right away.
No,
so and testing it in that example probably.
And even if people talk about getting slash dotted, or maybe you're on a popular talk show and you get mentioned live on air, and you think that everyone's going to at the same time hit the enter key and go to your website. Well, in reality, some people have the computer sitting on their couch, other people have to get up and walk over, and the reality is that even then, with some of the largest events, you'll see traffic ramp up.
It ramps
over time.
up. Yeah.
So your load test should absolutely reflect that. So this is not what your traffic graph should look like.
Yeah, that's the example, right?
Yeah. And you're just going to see problems if you're doing that. This is the same thing if you're driving a car and you're at a light and you say, okay, go 100 miles an hour. You don't pop the clutch and instantly go 100 miles an hour, right? You have to pull out of your spot, and you can go fast in a short amount of time, but take it easy. So something like this is a lot better. Kind of ramp it up, and if you really want to do it nice, you kind of smooth in and out of the traffic. So let's look at a basic recipe here. when you want to test traffic, let's say your goal is 1,000 QPS, 1,000 requests per second. If you were to just throw 1,000 on there, and even if you use that nice little curve from before, but let's say you have some inefficiencies in your app that you haven't worked through yet, and those inefficiencies would normally kind of kick up or start acting up at 20 requests per second. If you then throw 1,000 at it, you're not only going to see all the errors caused by the, going over the 20, but you're going to see all the kind of the snowball effect of that. And your error logs are just going to be a big mess, and you won't be able to tell what's going on because you've just completely overloaded kind of the contentious spots in your application. And so what we want to do is have a recipe where we get you to 1,000, which is your target, very quickly, but we kind of stop along the way to make sure that we're in good shape and we can handle that amount of traffic.
And so we're sort of progressively revealing maybe performance problems as you kind of go through. Maybe there's 5 or 6 different problems versus you see all 5 or 6 at once and you can't actually figure out what's going on.
That's exactly right. And I haven't met an application either that I wrote or anyone else that I know wrote. I'm sure there's people out there who write perfect applications the first time, but there's always kind of scenarios you haven't thought through. Maybe there's places where you said, oh, I'll come back and do that, and then you got distracted. And there's maybe some unknowns. So exactly, we want to find those problems, but we want to find them one at a time. Because the problems generally are really easy to address if you have just that one problem. If you have, for example, the global page counter, that problem is actually pretty easy to find if that's the only thing going on. So here's our recipe. We'll start out with something small, like 5 QPS, 5 requests per second, and we just keep sending 5 requests per second, and we look for any problems. If you actually had a global page counter, this would already show up at 5 QPS because entity groups are kind of designed to handle at least 1 QPS. Sometimes you can get a little bit more out of it, depending on whether you're master slave HRD. But 5 QPS is enough to find issues like that. And that's a small amount of traffic where you can actually just look through the logs and you can see things. But let's say you don't have any issues there. So what do? You wait about 15, 20 minutes, and what you're looking for is the dashboards in the admin console. You want to see essentially a number of flat lines. You want to see no quota denials, which you certainly won't see at this rate. A very low error rate. There's always going to maybe be some background error rate because you're in a large distributed system. You want to make sure that your task queues are keeping up. You may want to kind of ratchet up the number of concurrent requests there if you need to. And no elevated data store contention. So you don't want to see a number of data store errors. And so then what we do is we double our traffic. But we do it slowly over a period of several minutes. And what we're looking for is the next application bottleneck. Now, if everything goes smoothly, and again, we see these flat lines, very low error rate, no quota denials, task queues are keeping up, we just keep moving on, and we repeat and repeat until we reach that 1,000 QPS or that 30 QPS or whatever number we're kind of shooting for there. And once we're happy and we've gotten to the desired amount of traffic and we have a very stable, consistently performing application, then we plan our next feature and go through the load testing process again once we've rolled out kind of a major feature or done any refactoring in the application.
Is there a best practice in terms of how frequent you actually do these things? Or is it just sort of, when you're making a major change, you sort of do that? I'm not sure what.
I think there's always a trade-off. In an ideal world, you would have like a dedicated QA team, right? And they would run your application through the paces for every single release, and you'd make sure it works. I know many of you are you might be working by yourself or just with one colleague, and everything is a judgment call. Everything's a trade-off. If you spend a day on load testing, you don't get to write this feature. And so you really have to decide, did I do some major refactoring, or is this really just a tweak to the CSS of the site?
But it's definitely the type of thing, like if you're launching, you probably want to do a major load test
Absolutely.
run. But then post-launch, let's say you've ironed out and you got some minor features, maybe it's not, but maybe if you're changing the way you're storing your data or you're changing your queries, maybe that would require something like this.
Absolutely.
Yeah.
You should have a load test before you launch big.
Yeah.
And any type of refactoring work's important.
Make sure you have billing on.
Oh,
I mean,
yes.
Right, it was one of those other things that some people forget to turn on until the last minute.
Yeah, so that's a really good point there, because App Engine has these free quotas, but they're much more. Your application is much more throttled because it's living kind of in this free world. As soon as you turn on billing, some of those constraints come off, and your application is ready for some real traffic.
Okay, cool.
Yeah. So this slide is here is just to make a point about the difference between the amount of time that it takes in our infrastructure, or if you were running your own servers, to write to disk versus to write to memory over the network. When we start up building applications, almost every application needs some sort of persistence and storage. So we're always using the data store, writing data to disk. But we should really realize that if you're doing a lookup to disk, you'll lose at least 20 milliseconds. You might be closer to 50, or it might even be 100 milliseconds, depending on what's going on. But doing a lookup over the network, that can happen an order of 10x faster. So that's an order of magnitude faster. Now, if you're in a single request having to pull a number of pieces of data together, that's 20 milliseconds here, 50 milliseconds there, another 30 there, that pretty soon starts to add up to real change. Whereas if you're making a few calls to Memcache, you can make 10 of those, and you still are only up to the speed of one data store call.
Yeah.
Now, for Python users out there, I should just really make a call out to NDB, the new database API. It does this for you automatically. So it introduces a caching layer, and when you fetch from the data store, it automatically checks Memcache first. In fact, it has another layer in front of this that's even faster, which is the context memory of the instance.
Instance caching.
Yeah. And for Java users out there, there's Objectify, which has a caching scheme called Objectify Cache. And you can turn that on, it gets a lot of the same benefits.
Awesome.
Now, let's talk about free lunch. I know it's right here in Mountain View, it's not lunchtime yet, but this looks pretty tasty here.
It does look pretty good.
So how do you get a free lunch? There's this saying that there's no such thing as a free lunch, but I think there actually is. Let me talk about that. I just mentioned using Memcache, but another thing that many developers forget is to turn on or to use static resources. So there are a lot of files in your application which don't change, or change very infrequently. And you can turn those into static resources, and they get served through a different path in App Engine's infrastructure, a path that doesn't even take instance hours. So you're saving yourself instance hours. The responses are faster for your users, and ISPs and others downstream can cache this content as well.
So let's just say I'm hosting a website with some dynamic and static content. So like the images, static HTML, that stuff you could serve up.
Exactly. Put that in static resources.
Okay.
Yeah. And then even for your dynamic requests, let's say you have the home page which you dynamically put together, and you have the top things that just happened, and you have a little news snippet, and you have some other stuff going on. You say, well, I have to generate that dynamically. I can't do that statically. Well, in fact, you don't need that information probably to be up to the microsecond, up to date every single time a user requests the data. Maybe it can be a few seconds stale. Maybe you could, if you have a lot of traffic, only update the data every 20 seconds. Maybe every 2 minutes is enough. So if you set your cache control headers and say, this page content, as it's generated, is good for the next 2 minutes, then every user that comes in the next 2 minutes, they can take advantage of that cache content, get a much faster response, lower the load on your site, lower your instance hours, etc. Saves you bandwidth.
Very cool.
And that's where the free lunch comes in. When this content is cached downstream at ISP, say Ayin and I live in the same neighborhood and we have the same ISP, and I just went and fetched this page from this very popular website, and then a few minutes later, Ayin goes out and gets that same page. That request might never actually come over to App Engine. It might be served directly out of the ISP's cache, that's the free lunch right there.
Very cool. So this is really important for people that are hosting websites. Even if you're doing things like in the Chrome Web Store, we have a lot of people like hosting Chrome web apps that have all these static resources, and that's really where you should take note.
And even little bits of dynamic content, like you might have a leaderboard showing the top 5 players in your game. Well, that information doesn't change second by second.
Right. So maybe having a slightly out-of-date copy every 30 seconds or minute type of thing.
Exactly.
Might be okay.
Yep.
Very cool.
So just with some small tweaks, you can reduce the freshness of the data only a tiny bit, but perhaps gain very significantly. And the nice thing is that these caching benefits, they actually are much more prominent the larger your site is. The more traffic you're serving, the more users, the more opportunities these caches have to serve cache content. So these things kind of compound themselves. So a couple more best practices, and this is particularly geared towards those of you that are mobile developers out there, because you have clients out there, mobile devices, that are running your software. So maybe you've written an Android app, and these applications are under your control. And you can program them to call home, to request data from your application. So now instead of humans who are a little bit unpredictable and they'll log on to your site at different times of day, now you have all these Android devices out there in the wild, maybe spread out through your country or spread out around the world, and they are all synced to the same network time, and they all obey the same list of instructions. And what you have is actually a mini botnet that is wired up to connect to your application. So this traffic graph right here shows one of the bad things that can happen when, let's say you decide, I want my Android app to call home every day at, let's say, midnight. And you get a few users, you get your friends using it, it's fine. And then suddenly your application becomes a little bit popular, and now you have thousands of people using your application. So there's thousands of Android phones out there that all at midnight call home, call your application at the exact same time, requesting the same information. And so you get these crazy little spikes that happen. And so you want to avoid that. And it's quite easy to do. You simply want to kind of randomize the check-in times. So every client kind of picks a random time. And if you still want to do it at night, you can say, okay, between 2 and 4 a.m., pick a random time and then check in then. That's still a lot better than a single point in time. The other thing that, once people have kind of tackled that, is developers will have a built-in retry. So if everything's successful, fine, keep going on, pick a random time. But if the device encounters any kind of error, then maybe it retries, say, 2 minutes later. Well, what happens when your site goes down for maintenance, for example? So suddenly your site becomes available to all clients. And so they all start retrying on, let's say, a 2-minute schedule. And what you'll get is actually one of these heartbeat graphs where every 2 minutes, all these clients try at the same time to reach your site. But that's too much of an instantaneous and unrealistic load. And so many of these clients actually will get an error message again. So they'll retry 2 minutes later. And so you create this crazy little heartbeat. So pretty simple. Use something called exponential backoff, which is you basically do something like double the retry time every time you fail. So you retry after 2 minutes, then 4, then 8, then 16. And this way, you're over time reducing the load to your site, so eventually it will recover from your own little botnet. But the important thing that you shouldn't forget here is, again, the fuzz factor. You have to randomize it a bit. Otherwise, these heartbeats just become more spread out.
Yeah.
So there's a number of best practices. We have this article. It's great. It's kind of a checklist to go through of performance issues that you want to look at, and it gives you some tools to kind of adjust between performance and cost. For some of your applications, performance is the most important thing, and you're trying to get the most out of App Engine as far as serving resources as quickly as possible. For others of you, budget's a little bit more important, and you want to get more out of the resources that you have. And this article kind of shows you some of the trade-offs and is at least a checklist of things you should be aware of, and then you can dive deeper into each of the details there. Here's a list, for example, of ways to reduce instance hours, which is one of the primary cost primary sources of cost for applications. And there's the other one is data store. We kind of did an informal survey of how developers are using their data store, and what we find is that almost all developers are using the data store less efficiently than they could. One of the common ways to get data back is to use a query. In many cases, a query can be replaced by a direct fetch to an entity, which is half the work. Because a query involves first doing a scan to an index, then figuring out the keys, and then actually going fetching those keys. When you do a direct fetch for a key, you skip that first step entirely. Yeah. But even a fetch can be more efficient. If you only need to know the key of an entity, you can do a keys-only query.
There's projection queries now.
Projection queries, very good. Yep. Where you pull in not all the properties. You pull in only the properties you need.
Right. So if I have an entity with maybe 100 properties, but I only need 3 at the moment, I could just fetch those.
Yes,
those
exactly.
3, and the cost will reflect that.
Yeah, you'll get a small data store op instead of a large one, which there's a big difference there.
Yeah.
Now, a while back we introduced in the admin console some of these performance knobs, and you won't see these knobs, or you won't see all of them unless you turn billing on. So it's another reason to turn on billing. And these 4 knobs right here really represent a way of tuning cost versus performance. So a couple of the typical things that you'll do is if you want to make sure that your application is all warmed up and you're ready to serve a lot of traffic in a very short period of time, and that's the most important thing for you, then you probably want to raise min idle instances. And that means, that tells App Engine, that's a signal to App Engine to keep more instances warm and ready in case there's a sudden increase in traffic. On the other hand, if you're very cost sensitive and you'd rather App Engine not spin up another instance if it doesn't need to because there's a short little blip in traffic, you can increase the min pending latency. And that allows requests to sit in a pending queue a little while before they trigger a new instance to be started.
Right. But isn't it? I guess one of the things I see a lot of is that developers are always kind of fiddling with these, but sort of out of the box, don't we say that that's basically the settings that we give you by default are pretty much optimal to start with?
Absolutely.
You should try starting with those settings before you actually mess with the sliders, and then sort of tune your application after that.
Yes, that's a good point. These are advanced settings, and if you are having any trouble with your application, you should set these all back to automatic.
Automatic.
And test there, and then only when you kind of need something in addition to those.
Or maybe you need to control your costs a little bit, or start making some performance trade-offs. That's because I think that's the thing I see a lot of beginners or even intermediate people tweaking this without really understanding what's going on. And there's these side effects that they see in their application that as soon as they put the knobs back to automatic, they sort of go away. Yeah.
One of the when people reach out to us and say they have any issues with their application, if they suggested these settings, the very first thing we'll say is let's put them back. Let's do a load test or look at traffic with everything set to automatic, and then let's make some small adjustments from there. These are definitely not knobs that you swing from one extreme to the other. These are very fine tuning
Yeah.
for those advanced users and use cases.
And then the other thing I was going to ask is front-end instance class. So talk a little bit about that, because that's actually one thing in particular I'm always interested in, and I think a lot of developers wonder between, what's the difference between the F1 all the way up to the, in practice, what do you see?
Okay, that's a good point. So we have front ends and back ends. Back ends have instance classes called B1, B2, B4, and B8, and those represent different amounts of CPU and memory. And then on the front end, we have F1, F2, and F4, I believe, is the largest instance. So for most applications, the defaults of F1 are fine. But for certain types of applications, it can be very advantageous to actually switch to a higher class. And the reasons you would do this, a very simple one is if you need to have a lot of instance memory. Like there's a lot of state that you want to keep.
Yeah, I have a lot of data structures that I'm storing locally.
Exactly. So if you're running out of memory, that's kind of an automatic trigger. You need to be on a higher instance class, and that's kind of the easy case. The trickier one to understand is kind of the CPU one. So the way it works is when you have an F1 instance, think of it as having a fraction of a CPU. Kind of the way that we used to do time sharing. So in, say, a second, 1,000 milliseconds, you get kind of time slices within that for your request to be handled. Now, if you have multi-threading turned on, you actually have multiple requests going through your instance at the same time. But those requests, they run for a little bit, and then you can think of them as being paused and then running again if they're on an F1 class. Now, if your request, if you have a pretty simple application and you're not doing a lot of CPU, most of it's what we call I/O bound. So you get a request and you immediately make a call to the data store, and then you're just waiting for the data store to return, and then you put together a bunch of strings, template, and ship the result out. That's a very CPU unintensive application.
So F1's great, perfect for that.
F1's probably just great for that. Yeah. But if you're doing some computation or you're waiting less, there's less I/O going on, you may actually end up being CPU bound. That is, your application is ready to do some calculation, and then it's actually idled for a short while, and then comes back alive and idled again. And what's happening is your requests are thereby taking longer than they really need to. And so by switching to a higher instance class, you actually get a fuller fraction of the CPU. And that allows your request to actually keep running until it's finished and then immediately return. And so depending on your application, it may very well be that if you switch to, say, an F4 front-end class, even though those instance hours are more expensive, it may be cheaper to run your application on that instance class.
Because I can get more in that request versus maybe a bunch of F1s that would take me to sort of process.
Yeah, your request will finish sooner, which means in total you need fewer instances running to handle all your concurrent requests.
Now, would Appstats help me figure that out a little bit, or is that?
A little bit.
I'm trying to figure out how do you actually figure that out when I need to, or is it sort of just fiddling with it and sort of experimentation?
I think the best way of doing this is to actually change the instance hours in a controlled setting. So a load test is a great example. Run a load test, and once the load test is clean, like it's error-free, you figured out your bottlenecks, and now the thing is just running very smoothly.
I see.
Get one of these slow ramp-up load tests to your target, let's say that was 1,000 QPS, and you let it run for half an hour on F1s, and you let it do the same thing over again, you run it for a half hour on F4s, and just see what the instance hours looks like, what the costs look like.
I could look at the request latency and probably some other things. Just to sort of
the cost might be identical, but your clients might receive responses more quickly, so your users are happier, means more usage to your site, maybe more traffic, more revenue.
Very cool.
Yep. So that's a great feature that people need to look at. And also the PageSpeed service, which we launched at Google I/O, takes care of all these static resource optimizations, rewriting HTML and CSS and JavaScript, and just optimizing the resources.
So that's sort of one level further than the kind of the original caching we talked about, where it actually introspects into your HTML, CSS, JavaScript, and rewrites stuff for you.
Exactly. It takes all the white space out. It takes the comments out. It can actually change the JavaScript and take these long variable names and squish them down to little ones, making things more efficient. It has a number of default settings, default rewriters. But if you do some experimentation, there's some optional ones that you can turn on that will actually inline more JavaScript more aggressively. So the way the PageSpeed service works is there's say 20 rewriters, and each one has a specific capability. There's a CSS rewriter that gets rid of white space and comments, and gets rid of CSS that is kind of orphaned, things that won't do anything. There's a HTML rewriter, there's a JavaScript rewriter. And then there's, so a number of those are generally safe and they're turned on by default. And there's some that are potentially unsafe, depending on your application. And those you can turn on manually after you've confirmed that they basically don't hurt your application. And if you turn all the kind of aggressive options on, you can really get some nice improvements as far as kind of response times from your application.
Very cool. Before you go to the next slide, I just wanted to remind everyone that's watching us live, we're going to go to questions in a bit. So if you do have specific performance questions that you want Fred and I to talk about, go ahead and put them in the moderator link. Now would be a great time to do that, and then in a few minutes we'll kind of go through the questions. So.
Great.
Sorry, just
no, that's good. We
questions.
want more. We want more of your questions. We're here to answer them for you. Now, one thing to not forget. And I know the way that happens with presentations is you hear a lot of this stuff and you kind of remember the first thing that was said and the last thing that was said. So one of the last slides here, I want to make sure it'd be one of the things you would remember, which is to enable warm-up requests. And App Engine Scheduler has this job of trying to predict what your traffic is going to look like, say, a second from now. So it looks at all the traffic that's coming in, it looks at all the requests that are in flight, and what the average latency or the average response time of those requests is. And then it tries to predict whether it will soon, momentarily, need a new instance or not. But it can only warm up instances in advance if it either, if it predicts so or you tell it so with min-idle instances, and only if you enable warm-up requests. Now, warm-up requests are kind of a special internal request that App Engine will send to new instances of your application to make them ready to serve live traffic. Without this, you'll have what we call a cold instance, one that hasn't seen any traffic yet, hasn't been initialized. And one of your user requests is going to come to your site and say, I'd like the home page, please. This request will go to this cold instance, and that request is going to have to sit there and wait for your application to initialize. Maybe you fetch some global data and you have to make a few round trips to the data store and collect a few things and kind of get your house of cards in order before you're able to serve that response. That's all time that your client is waiting. When you have a warm-up request, App Engine can, without affecting user latency, send a special little request to your application. Your application can initialize kind of quietly behind the scenes. And then when it's all ready to go, it's nice and hot, then the first user request comes along and hits that instance. So be sure to enable warm-up requests. When you have them, you'll see these requests in the log, /_ah/warmup. There's some default behavior that you can read. Particularly, this is enabled by default in Java, but disabled for Python. So in Python, you definitely want to turn that on manually. And then there's some ways to override the servlet handler there for Java applications. Now, I said that was the last thing. There's one little tiny tip here, which is avoid the default error message pages. When you have problems with your application, you can define your own error pages. Both in Java and Python, it's pretty simple. Just a few lines of configuration, and you point it at a nice, pretty file.
So you can make a beautiful error page.
You can make a beautiful error page. Maybe one with kind of a robot that's all broken in parts or something like that.
Very cool.
So, I think we have some questions lined up.
Yeah, there are some questions. So I'm going to go ahead and go to the moderator, and I'll just read through the ones we have, and we'll try to answer them as best we can.
Okay.
So I'll just read them out to you, Fred. So here's one from DP in Italy, which is, do task queues influence performance? Any tips about task queue performances?
There's a lot to say about task queues. So the way we kind of refer to requests, there's two types. We have online requests and offline. Online is anything user-facing. So a client coming in making a live request. Kind of think of it as a live body or a hot Android device kind of behind that request. And then offline requests are all the kind of the background stuff. So that's task queue and cron. And App Engine, the App Engine scheduler treats online requests and offline requests a little bit separately. It knows that that you might have offline requests that are a lot slower than online ones. In fact, if you have any kind of slow operation, you should probably move it to a task queue so that your online requests stay nice and fast. But App Engine will treat those two classes of requests differently. In fact, it will look at the different queues that you have. So if you have a named queue, foo, and another queue named bar, and they have different performance characteristics, App Engine will kind of, the schedule will take care of them separately. There are a number of knobs that you can tune in the queues.yaml in Python or the App Engine queue.xml in Java.
Yeah.
You can configure the maximum rate of each queue, I think up to 100 requests per second.
100's the max, yeah.
And then you can also configure, I believe, the number of concurrent requests. At least there's
a rate, and then there's a bucket size and something.
Yeah,
there's
buckets of refill size.
Yeah.
We have a nice link to a Wikipedia article about bucket counters and how they work. But the main thing there is you can crank up the rate.
Yeah. And I'd also say, I think we did a couple of Hangouts recently, specifically on task queues. Amy did one, and then I think
that was a good one, yeah.
Danny did one as well. So there's some good, you should look at Hangout resources recently that we've done specifically to task queues, I think, that are pretty helpful.
But I think to come back to the main question, you shouldn't worry about tasks influencing the performance of your online requests.
So they're sort of orthogonal.
Yeah, so what you do in the background in batch shouldn't negatively impact kind of the user experience. In fact, I would almost say the reverse, that, or say, sorry, something different, which is anything that is slow in your online requests. So if you have a request that takes a long time, you should almost always see if you can move that perhaps to a task and respond back to the client more quickly. Because what you want on the front end is really performant requests, and on the back end you kind of want these slow batch things. I hope that answers the question.
Okay, cool. Yeah, all right, let's go. There's a couple new ones popped up here. One we'll just deal with real quick, which is from Anonymous. Are there any plans to create cloud endpoint generation scripts for Python with proto-RPC? So this is just a random App Engine question, but it's related to cloud endpoints. I don't know the answer to that question. Dan Holyvote, who is running the Trusted Tester program for cloud endpoints, will be happy to answer that question. So if you're not already in the Trusted Tester program for cloud endpoints, go ahead and join, and Dan can answer your question there. There's a whole forum set up for that.
Yep.
Good question. Okay, here we go. Here's one from Nelson in San Francisco, which is, this is a Python one. So how does the number of WSGI app instances affect performance? Is it generally better to try to bundle URL routes into a fewer number of apps, or split URL routes across multiple app instances?
Across multiple app instances. Oh, I would say that doesn't really matter. What does matter is perhaps the overall memory footprint of your instance. So if you're duplicating some data across those app instances, that's not going to help. Although in most cases, it probably won't matter, because you're probably not hitting an instance threshold of your F1 class or F2 class.
Right.
These types of tweaks are unlikely to really help.
Yeah.
What you do want to do is absolutely make sure that you have thread safe set to true, so you have multi-threading enabled for Python. That only works on Python 2.7, of course. You should be using Python 2.7, which is better at kind of scheduling.
Yeah, I agree. I think it's that you don't really gain anything.
Yeah, don't worry about it. Organize your code, especially in Python, for the way that makes sense and productive for you. The big things to worry about are enable multi-threading, using Python 2.7, using the task queue where you can. The really big hits that you can do are those data store performance tips, like doing fetches instead of queries, and wherever you're making a call to another like Appengine backend service, whether it's Memcache or data store or even URL fetch, do those asynchronously if you can, if you're doing multiple, so that you can do them in parallel. If you need to fetch 5 things from another web service, issue those 5 calls via an async call, and then wait for the response. And all 5 will happen at once, rather than sequentially. Those are the big wins.
Yep. Okay, here's another question from Nelson. This is sort of a general purpose question, which is it possible for App Engine to release global stats for some benchmarks to help drive design and modeling of applications? So for example, what's the average upper bound for entity write ops? Is 20 write ops average for an entity with n properties? Is 42 high? So I don't know what the guidance is on like specific bounds. And
so these sorts of things really depend on the types of application you have. You can take some hints from our examples and the way our APIs are going. So if you look at in Python the DB API versus NDB, you see that in NDB, the newer API, we support structured properties, which are kind of nested properties within a single entity group. I think we've done a better job now at telling you to make sure that your properties are not indexed by default, because you have all the extra cost of the data store writes every time you update the properties. We've added support for projection queries so that you don't have to fetch all the properties from the data store. So you see some strong hints there that more properties are definitely expensive. We have support for list properties, which is a way of kind of efficiently packing things. So I'm not sure that those statistics would be that useful. But the practical advice of fewer properties, fetch only what you need, do it as efficiently as possible, pick your keys, turn off indexes for things you don't need. All of those things will have fairly big impacts. But at the end of the day, if you need another property on an entity, you should have it.
Right.
What you should be wary of is, lots and lots of properties, lots and lots of indexes. If you get anywhere close to the limits of, I think you can have 200 custom indexes on an application or something like that.
Yeah.
If you're anywhere even in the ballpark of that, you probably need not organizing your application the way you want. You may actually have an application that's more suited for using Cloud SQL rather than the data store, which you can do in App Engine. You can use a SQL instance that will allow you the relational queries and the indexes that you need.
Right. Okay, let's see, we have about 5 minutes, so we have a couple short ones here, and then there's kind of a bigger one we can deal with at the end. One is, should you be doing async calls in deferred/offline tasks too?
If it allows you to do things in parallel, absolutely yes. Yeah. So when you can make 2 URL fetch calls at once instead of after each other sequentially, or you can do a batch get from Memcache to fetch 3 keys instead of fetching one after the other, those are always beneficial. The number of instance hours that your application needs is, in an ideal world, is very simple to calculate. You look at the average response time for a request. Let's say it's 100 milliseconds. And if you were in a single-threaded environment, that means you can handle 10 requests per second per instance. Now with multi-threading, you can do a little bit more. In the real world, your input traffic is a little more what we call stochastic or random. Requests don't come in like a heartbeat, where every 100 milliseconds you have a new user coming in. They come in kind of bursts, and there's some peaks and valleys. And so the scheduler has to deal with kind of those inefficiencies, and your application does. But your goal as a developer is really to make your requests finish as quickly as possible. That means doing things in parallel, doing things efficiently, and the faster you get done, the happier users will be, the fewer instance hours you will need, the more efficient the scheduler can be. So
cool. Okay, here's a question from Joachim in Sweden, which is, are there any gains in speed to be made by rearranging the filters of a merge join query? I don't know the answer to this one, actually.
There are, so I'm probably not the best person to answer that, but I will say one thing that would matter, which is when you, in the dev app server, when you run different queries, it will automatically update your index.yaml or your app engine indexes.xml, and it will put all the custom indexes that you need in there. Now, each of those indexes has a write cost associated with it for all the properties that are referenced in that index. If you set up your filters and your queries in such a way that you somehow are able to reuse some of the indexes, then anytime you do a write to any of those entities affected, you would have fewer writes, and those costs could potentially be significant or at least noticeable. I'm not sure that it matters too much to rearrange the filter operations within a single query, but it certainly helps to think globally about the types of indexes that you have, and to see where you can have reuse and have fewer index writes.
Yeah. Yeah, for sure. And by the way, this is a great question to post on Stack Overflow. So a lot of our team actually monitors Stack Overflow, as does some of the engineering team. So this would, if you're not satisfied with this answer, I'd put it on Stack Overflow using the Google App Engine tag.
Yeah, that's a good one for kind of an in-depth analysis discussion. And
yeah, this is a really good one to talk about there. So we have time for one last question. Basically, there's a discussion in the public App Engine group related to deadline exceeded exceptions for big jar files. So I think this is like loading. And the gist of the question is, well, what are the conclusions? And I guess you have to look at the thread, and we probably don't have time to do that right now. But it looks, the subject is Java instance startup time, and I think it's related to having big jar files and some errors that can cause you upon loading requests and so forth.
Okay. I think this is actually probably another good question for Stack Overflow. This is also a question where the answer 6 months ago probably would have been a little different than it is today. We've done a number of things to really help Java applications out on during their startup and initialization. It still remains true that the fewer jar files you have, the less work that you do in initialization, the more that you turn on warm-up requests. These things will help. App Engine is a little bit different from a lot of infrastructure that many of us are used to for like on-premise and infrastructure as a service, in that there's a lot of popular, let me say it this way, there's a lot of popular Java frameworks that were built and designed when the way to run a web service or an application was to have a number of servers, let's say 5 servers, and they all start up, and it's okay for them to take 5-10 minutes to physically start up all the way up and running, and then to leave them running for days or weeks, and do occasional maintenance windows. On Sunday night we'll shut down for a few hours. App Engine is a very different environment where we're constantly spinning up new instances to handle new traffic, shutting others down. There's more than 100,000 applications on App Engine right now that are all kind of vying for the same resource and shared resources. So the kind of engineering trade-offs are a little bit different. We're looking for very fast startup so that we can kind of adjust the scheduler very in a fine-grained manner to adjust to your traffic. Now, if you have one of these applications that uses these kind of heavier frameworks that just need longer initialization time, they really come from, I don't want to say an era of, but a time not that long ago where these are the types of frameworks that we used. App Engine does have some knobs for you. Those performance tuning knobs I mentioned before, there's that min idle instances. And if you enable warm-up requests and you just crank up the min idle instances, maybe even just a little bit, App Engine will always keep however many you specify instances ready that are pre-warmed up, ready to take on new traffic, not having to wait for the initialization time. In the extreme case, there's kind of an advanced tip that I can go into, and if this is not for everyone, but this is one kind of technique that you can use. If you have an application that really wants to do a lot of startup initialization, and it's going to take you even more than the 60 seconds, and you've exhausted like min idle instances, for those Java applications, be sure you're trying the F4 front-end instances, or even starting up maybe a backend instance and doing a B8, because it'll give you more CPU, start up more quickly. If you've exhausted all of that, there is a technique that you can use, which is when you receive your first request, do some of the initialization. Let's say do half the work that you can, and you set a little global flag in a static variable and say, okay, I've done the first half of my initialization. And then instead of returning the response, because you know you're not fully initialized, you actually send back a 302 redirect to the client. And you tell it to go back to the exact same URL that it just requested. So that client gets the redirect response, and it will just send that request again. And hopefully it will hit a different instance that's already warm and the client's taken care of. If it's unlucky enough to hit the same instance that's still all right, now your instance has gotten the second request, but it's had those 60 seconds to kind of do the first half of the warm-up. You look at the static variable, go, oh, I need to do the second half of my initialization. You do that, and then you serve your response.
That's tricky.
So it's a complex case, but what we're really doing here is we're saying, well, the initialization time of your application, because of the frameworks you're using and what you're doing, you might, if you add that plus the time it takes to handle individual response, those two together, if they exceed that 60-second limit on an F4 class instance, then this is a technique to break those apart. The warm-up request tries to break out the first part from the second. This kind of advanced technique I described is a way to take that initial part and even break that further down into pieces. So those are tricks that you can use.
Very awesome.
But higher instance classes can definitely help there.
Yep. So
that's what they're there for.
Perfect. Awesome. I think we're out of time.
Okay. Well, thank
you for having me, Fred.
Today.
Yeah.
And thank you for all your questions. Really appreciate it, and hope to be back soon.
Okay, and we'll see you next week. And be sure to check out Stack Overflow as well as a great resource for questions and answers.
We're all there.